Hello class, me and Jeremy are here today to explain correlation coefficient and chi-squared. So, first we will need a data set. Here's our data set. We are comparing the height of a person, which is in this column, compared to their shoe size, which is in this column. So,
we could just pan down. What exactly has happened here? Maybe you can just explain to people, point out all the stuff for Frapp.
Pretty much, correlation coefficient helps you find a relationship between two things to see if they're correlated with each other. And chi-squared helps you find out if two things are dependent on each other, or if they're not, or not.
Today, Junior?
And another statistical analysis is line of best fit, which can help you make predictions about data to further make hypotheses about said data.
Correlation coefficient finds the direction over strength and puts it all into one value, which is the R value. So first we divide by the total number of which total numbers that there are, and since we don't want to have three parts of the fraction, we just do 1 over n and multiply it by that. Then we find the sum of each x point, which is from our data set, and divide it by the x bar, which represents the mean of all the x's combined. And then we do the same for the y value, and we multiply these. We then divide it by the standard deviation, which gives us the spread of the data to put into context of how far apart they are from each other, which gives us the strength of it, because depending on how far apart they are, we can tell how strong the correlation is. Our data, the x bar is 68.7, the y bar is 11.03. The standard deviation for x is 5.49, and standard deviation for y is 2.4. So the easy part is multiplying these two, which we did down here, 5.49 times 2.4. Now going with our original equation, we first divided 26, which is a total number, by 1, and multiplied it by this total number here. And then we took each x point, which in this case would be 60, divided by 68.7, ended that parentheses, and multiplied that by the same thing for the corresponding y point. And that gives us the direction strength, or the direction for one of them. Then we add this to each point, and then we divide the total of that by 5.49 times 2.4. In this case would equal 0.92, indicating that the strength and the direction of this is very strong. And therefore we can say that although we can't determine causality, we can determine that there's a strong correlation between shoe size and height. Where to determine whether if something is significant, the difference between them, we determine first the frequency of observed values, we subtract that from the frequency of expected values, and then we square that, and we divide it again by the frequency of expected values to put it into context of the total set of data. And then we add this up for each one, and we get our total chi-squared value. So find the frequency of observed would give us what we actually had, and then we subtract it by what we should have gotten if everything was independent. We then subtract this and square it, so we get a positive number, and we find the difference, obviously, and then we divide it by the expected value, so we know how far apart it is, because the difference between it being 3 off, if there's a total of 30, is much more than if there's a difference of 3 and it's out of 3,000. Therefore, the difference here would be less significant, and that's why we divide by the frequency of expected values. For our data, we categorize it by the mean, since there's no natural cutoff and we don't want to have any other biases. So therefore, the mean of the shoe size of the height was 68.7 inches. So in this part, we did x is greater than, and this part x is less than or equal to. And for the y value, we did the same thing. So here, we can see the frequency of our observed values. So for example, there's 6 people that had a height that was greater than 68.7 inches, and that had a shoe size that was greater than 11.03, which isn't an actual size, but for the sake of the mean, that's what it is. So then to find the independent probability of each one, what it would be, we take this number, which is 11, we divide it by the total number, which in this case is 26, and we multiply it, due to the rules of independent probability, by adding these two up and dividing that by 30, which would give us 9 over 26. Then this gives us the percentage of what the total it would be if this had been completely independent. And so therefore we multiply by 26 to see what number that would have actually been. In this case, that number would have been 3.8. we have all these numbers: 3.8, 5.2, 7.2, and 9.8, which are all the frequency of expected values. So then, referring to our general equation here, for example, for the first one, we do 6 minus 3.8, which is the corresponding frequency of expected values, square that, and divide it by 3.8. We would then do this for each box, so we would have 4 total, add those all up, and this would give us our chi-squared value, which in this case is 7.26. Then we compare it to our critical value. To do that, we need to know the degrees of freedom, which is the number of columns minus 1 times the number of rows minus 1. In this case, it's 2 minus 1 times 2 minus 1, so it's 1 total. The critical value there is 3.841. Since this number is greater than the critical value, at the 5% level of significance, we can determine accept the alternative hypothesis, which would state that height and shoe size are dependent upon each other, as opposed to the null hypothesis, which would say that they are independent of each other.
It's very fragile. It's like a baby panda egg.
Well, thanks much, Riff Raff. Keep on rocking in the free world and do-do-do-do-do.
Do. Going down.